Dukes, talking about fractional decompositions and Latin squares.
Okay, thank you for coming to the talk. And here's an overview of the talk. So first, I want to tell you about graph decompositions. It's a favorite topic of mine. Give you a reminder of the definitions and state of the art there as far as the problem that I'm interested in. And then tell you a bit about Latin squares, also probably familiar to everybody, but just sort of set up the direction we're heading. The main result that I want to talk about is a guarantee on completing partial Latin squares under a certain assumption that they're not too filled. Okay, so that's sort of where we're heading. And then in the sketch of the proof, this is where the algebraic graph theory sort of comes in. So I want to tell you a bit about how the method of the proof works, sort of marrying perturbation of linear systems with some of the algebraic graph theory that involves the line graph of KNNN, the complete three-part type graph. So I'll show you how all that connects together, hopefully. Okay, so the main kind of definition to keep in mind is that of a H decomposition of G, where H is a small graph, maybe. Think of it as like a tile, and G is a large graph. And think of it as probably fairly dense for our purposes. So lots of edges and fairly large as well. So an H decomposition of G is just what it sort of sounds like. It's a partition of the edge set of our graph G into subgraphs isomorphic to H. So here you can see this sort of triangle with an extra edge H, two copies of it use up with no overlap the edges of G. So it's sort of a tiling in this way. All right, so there's obviously some arithmetic conditions that need to be satisfied. You need the number of edges of your tile to divide the number of edges of the graph into which you want to decompose into this H. So E of G, cardinality of E of G divides cardinality of E of H. But also locally, there's a condition that you have to be able to form the neighborhoods in your host graph G by, well, you have to be able to form it from neighborhoods in the tile. And so the GCD of the degrees in the tile has to divide the GCD, has to divide the degree of every vertex in G. There's another condition that I'm quite interested in, but it won't show up really here today. Just thought I'd mention it though along the way, that you need to be able to form, this is in characteristic 0, so not really an arithmetic condition, but you need to be able to form G from as a non-negative, maybe fractional linear combination of copies of H. So I guess it does sort of connect to today in the sense that I want to soon show you a fractional relaxation of the decomposition. And you certainly need to have a fractional decomposition that is allowing possibly half of this copy of H and half of that copy of H to use up this edge that they share exactly once, for example. So very roughly, the condition here is that there just has to be sort of a rich enough supply of tiles in G to be able to pull from in order to form the tiling. Okay, so that's a little extra condition. But yeah, I mean, sort of in this direction of the fractional decomposition. So the fractional relaxation of the decomposition problem is just we want to take an assignment of positive real numbers to, or if you like, non-negative reals, taking all possible copies of H, which I've indicated here with HI. So for each HI, a copy of H and G, you take a weight. And you'd like the sum of the weights on every edge to be equal to 1. And that would, I mean, that's, I guess, a sensible fractional relaxation of our condition of having an H decomposition. Here's an example of a fractional decomposition. So say you've got a 5-cycle G and a path on 2 edges, which I should probably have called P3, sorry. anyhow, the path on two edges, although I mean clearly it violates the necessary global divisibility condition that the number of edges in it certainly does not divide the number of edges of our graph, which is 5. We can nonetheless take half of the path on two edges, kind of spin it around in a 5 cycle, and have every edge occurring exactly once in this fractional setting. So hopefully that makes sense. I'm just going to make sure my pen is doing what it needs to in case I need to write something here. Okay, so now a conjecture concerning triangle decompositions, so K3 decompositions, which turns out to be maybe one of the first interesting cases, I guess. All right, so here H has been specified to be K3, specialized to the case K3. So the conjecture says that if you have a Eulerian graph, which just means basically we have to have just think an even degree at each vertex. If the minimum degree is at least 3n over 4, where n is the order of the graph, then, and you need to have, of course, the number of edges a multiple of 3, then this conjecture says that G has a triangle decomposition under those assumptions. So basically, it just has to have the arithmetic conditions hold and minimum degree at least 75% of the complete graph. Okay, and then this is, but currently even the fractional relaxation is unsettled, but there is something getting pretty close now to this. If you replace 3/4 with 0.827, then a result of Delcourt and Postle says that that the fractional triangle decomposition exists under these assumptions. And then due to some marvelous machinery of Barber, Kühn, and Osthus from a few years prior, they set it up so that if you can get a threshold for the fractional problem, then they can basically cross out the word fractional. So together, these two results, these two papers, I guess, establish Nash-Williams. I should say you cross out the word fractional, but of course now you have to impose the arithmetic conditions. You need to now have the divisibility conditions. Every degree should be even because remember a triangle has even degree, and so remember that that local arithmetic condition would say that the degrees in your graph should be even in order to have a triangle decomposition. Okay, so assume that, and also assume number of edges a multiple of 3. Then these two papers in conjunction establish the threshold of 0.827, which is getting toward the 0.75 that would be needed for the conjecture. Okay, so that's the status for sort of situation of dense graphs. And I want to talk today about a partite version, a 3-partite version of this, which is useful for Latin squares and the completion problem of Latin squares. So a Latin square of order n, remember this is just an n by n array filled with n symbols, so that every row and column is a permutation of the symbol set. Here are a couple of Latin squares with a bit different structure. You see kind of a sort of a 2x2 sort of fractal type thing on the left, and then on the right there's a circulant Latin square of order 5, and so, yeah, Latin square certainly exists, so you can complete an empty Latin square. But I want to connect that with the graph decomposition soon here. First, though, just the sort of the problem we're interested in is completing partial Latin squares. This is probably sort of clear to you because it's you know, kind of familiar probably if you've solved a Sudoku. You're trying to basically this is the process Sudoku, but without the block constraints that are in Sudoku. We want to just finish filling in the symbols of a partially filled Latin square, where a partial Latin square is just, so a priori it need not be completable. We just have to have it either every cell filled with an integer from 1 to n, or blank, where we haven't yet violated the property of being a Latin square. That is, we don't have 2 of the same symbol occurring in any row or column together. So that's a partial Latin square. And a completion is just what you think. You take your pencil out and you solve the Sudoku. Okay, so there's a completion of the partial Latin square we had before. And even if it's fairly sparsely filled, you can see that maybe there's no way to complete a partial Latin square. So this is a valid partial Latin square. I mean, just you wouldn't want to see it in a Sudoku magazine. There's nothing to put here, right? We can't put a 4. Well, we kind of need to put a 4 because of the first row, but we can't because 4 is already occupied in the 4th column. So we can't always complete. So the question is, well, are there good sufficient conditions on completing partial Latin squares? Roughly speaking, the direction we're going to go is that we can, when no row or column or symbol is overused, and we'll specify what overused means. But here, the first row has been, highly overused, and so we'd like to not use that first row that much. And if we don't use any row or column or symbol very often, then we can show we can complete. And maybe that's not, or that's probably quite unsurprising to you that if it's that sparse, we should be able to finish the job. Okay, so a little bit of background on completing partial Latin squares in general, kind of even out of the context that I'll be looking at today. A famous theorem, it's sort of the theorem in sort of undergraduate combinatorics, whether you think Hall's theorem and network flows or Koenig's theorem. There's lots of variations of this, but if you have a Latin rectangle, then you can always extend by a row, basically add pull out another one factor out of the complete bipartite graph that's sort of implied to be left over, and keep doing this, and you can complete a partial Latin square whose filled cells form a rectangle. By the way, even if that rectangle is not the full width, you can also do that. Provided a mild assumption on how much has been filled in. As long as you can extend the rectangle to the full width, then you can continue the rectangle down row by row. Also, the solution of so-called Evans conjecture from Smetaniuk, 1981, says that if you don't have very many cells at all filled in, so at most n-1, which by the way, that's just sort of one less than this sort of counterexample. In general, you could load up the first row 1 through n-1 and then put an n devilishly off the first row. So that's filling it with n-filled cells so as to spoil the completion. But if you go one less than that, then this Smetaniuk result says that you can also complete. And then toward the sort of local or sort of sparseness condition row, column, and symbol, if no row, column, or symbol is used more than epsilon n times, and this epsilon is the sort of thing we'd like to dial today, hopefully raise it up a little bit. If epsilon is 10 to the minus 7, well, this was done by results in Gustafson's thesis from 1991. I believe that was the first. Well, there was some early work in the 80s from Hagfist and Chetwynd and Hilton, I think, but maybe there was some extra conditions, and epsilon was even smaller. Anyhow, epsilon was raised to 10 to the minus 4 by Bartlett in his 2013 thesis, and you can't raise it past 1/4, and that's going to kind of connect with this Nash-Williams that we saw before, where remember 3/4 was the barrier that was conjectured there. I didn't mention it verbally, but I think it was on the slide that you can get a counterexample below 3/4 for the dense graph setting, and there are also counterexamples for the partial Latin square completion slightly above 1/4 density, where density, I hope you understand, is implied by the this sort of statement that no row, column, or symbol is used that often. Okay, so connecting the two ideas together, graph decompositions and Latin squares. And I'm sorry, I haven't yet said anything about the algebra, but I hope to spend some time on that. Completion of a partial Latin square is equivalent to a triangle decomposition of the sort of, subgraph defined by leftover row, column, and symbol instances. On the left, we have a partial Latin square. It's actually almost done, right? And on the right, there is a three-partite. So there's this three-partite graph that I've defined as follows. So there are n where in this case 4 rows, each partite set has size 4 because there are 4 rows and columns and symbols, and 4 is the order of my partial Latin square P over on the left. Okay, so the partite sets are indexed by rows, columns, symbols. Let me rephrase that. Rows, columns, and symbols define partite sets with n vertices each. And then we join row I and column J if the corresponding cell is empty. And we join row I and symbol K if K does not appear in row I, and likewise for column J and symbol K if K does not appear in column J. This graph is probably familiar to anyone who's worked on a hard Sudoku, I guess. This is the kind of graph you need to work out to be able to figure out what to do to solve your Sudoku. Now, in this case, it's kind of clear. You can sort of see this thing falling apart into triangles. But if we are to be able to complete our Sudoku by actually putting symbols in the remaining empty cells so that everything works, well, we need to be able to put in a triangle at a time, because of course, when we fill a 2, say in this corner, well, that's saying I have to pick row 1, column 1, and symbol 2 all at once, and so I use up that triangle of edges in the missing edge graph. Okay. Anyhow, so I think I picked a different 2 there. So okay, a different example of a choice of a triangle to complete the Latin square. Okay, so that's okay. So I guess that maybe sets up a correspondence between triangle decompositions, but in the 3-partite setting, where now we have rows, columns, and symbols indexing the partite set, and the completion of partial Latin squares. So if you're a puzzle solver, maybe the 3-partite version of the triangle decomposition problem is nicely motivated. Okay. I need to define a sort of an annoying little piece of terminology in order to state the main result. So the divisibility conditions that were present for triangle decompositions, remember hypotheses in that Nash-Williams conjecture, or the Delcourt and Postle almost verification of it. We don't have those divisibility conditions here in the same way, but we do have an important condition that our 3-partite graph, which is modeling the partial Latin square, but in any case, if you want to try to triangle decompose complete 3-partite graph, then you should have that graph be locally balanced. And that's because triangles have to touch each partite set exactly once, right? So locally balanced just means here that for any vertex, chosen one in the diagram here, the number of edges sort of cyclically to the right should equal the number of edges to the left. So the kind of in degree equals out degree, if you want to kind of put arrows on these things. But this is certainly a necessary condition for there to be a triangle decomposition. Okay, so with that definition in place, now the main result is, which hopefully I can open up the proof a little bit in the remaining time, but every large enough, although you don't have to be too large for the fractional problem, but if you have a sufficiently large, locally balanced 3-partite graph where the minimum degree is about 4% under complete, so 0.96 times the degree that would be in the complete 3-partite graph. That's why I wrote it this way. Then you get a fractional K3 decomposition, and because of I actually, when Barber, Kühn, and Osthus proved the result on sort of defractionalizing with the method of absorbers, fractional triangle decompositions in the dense graph setting, I encouraged them, or Derek Osthus anyway, I wrote to him and said, you know, it would be great to have an analog of this for the partite setting. And there's lots of precedents, I think, in extremal graph theory for partite analogs of results. that are proved in a dense setting, and they took up the challenge, and they have the technology now to basically erase the word fractional given this threshold of 0.96. So together, their absorber work and the fractional result says that you can then complete partial Latin squares of order n where no row, column, or symbol is used more than 4% of the time. Of course, okay, maybe I should have said it has to be large in order for this to be true, very large, impractically large. You wouldn't be able to fit it in a magazine of Sudoku puzzle. But in case you were concerned that you might not be able to complete a partially filled Latin square, well, have no fear. Now we're trying to raise the 0.04, of course, to the conjectured threshold of 0.25, but this is a bit of an improvement from the 10 to the minus 4, which was the state of the art before. Okay, so now I should just say a lot of the work that's been done on getting good thresholds, like the Delcourt and Postle result, or some other work that came before it. A lot of that work is sort of combinatorial in nature and involves some gadgets and some counting. And in the case of actually a main piece of technology introduced by Francois Dross was what was using setting up basically a network flow problem that modeled the triangle decomposition problem for, so network flows were used. Anyhow, I want to hopefully highlight what I think is a cool use of algebraic methods for this problem. And I think the reason why they're the most successful, at least presently, to my knowledge anyway, this work is a little bit old, by the way. I'm sorry, it's a bit old. But I have actually told Sophia I have more new things to speak about coming up soon, but this was sort of the closest thing that I thought would be interesting for this seminar. Anyhow, I guess the algebraic methods probably work well here because it's hard to fit in a lot of gadgets into your three-partite graph to make some improvements, I guess, to a lot of the fractional triangle decomposition work. Sort of begins by saying, okay, assume you have every triangle with equal weight, and then let's try to move around the weights so that we can actually get it say no negative weight on a triangle. So moving around weights subject to some capacity conditions, I guess, is one way to think of the problem. But it's hard to move around. You're kind of locked in this three-partite setting. Although Richard Montgomery does have some sort of gadgets to move around, but they don't do quite so well for sort of three-partite version. Although I think maybe asymptotically as the if you change to cliques of size k instead of 3, then when k gets bigger, the gadget has more kind of flexibility. Okay, let's get into the algebra a bit here. I hope the setup is clear, and I'm sorry it took so long. But okay, so we have a graph G, and the set of all triangles in G will be denoted by T of G. And W sub G is just this kind of inclusion matrix of edges versus triangles. So rows indexed by E of G, columns indexed by T of G, the triangles, and we, in the little e, little t entry, we put a 1 if E is an edge in that triangle and otherwise 0. Okay, now, the way I initially thought about fractional decompositions was just simply via this sort of naive linear system here. We just want to solve for non-negative vector x, entry-wise non-negative vector x. We want to solve the inclusion matrix of edges versus triangles times this vector of variables, which sort of, if you think about it, x kind of would tell you, I mean, there's x is this column here, and it's going to tell you what the weights are to use on the triangles in G, so that in total, every edge has weight 1. And this bold 1 thing here is, of course, the all ones vector. Okay, so I also think it's natural to just say, well, what if we just had the complete three-partite graph there as our graph? Well, I mean, every edge is in the same number of triangles. So you could just take a constant vector and solve, namely 1 over n times the all ones vector. That vector x solves this linear system. So when our graph has all the edges, it's sort of easy. Now, that's not how you'd make an actual Latin square, by the way. You wouldn't say, oh, I want to put 1 over n of every symbol in every cell. But in the fractional setting, you're allowed to do that. Okay, so that's kind of the sort of cheap way to get a fractional Latin square, right? Put 1/n of every symbol in every cell. And if you read every row and column and every row and column, you'll see every symbol exactly the right number of times fractionally. Okay. All right. So we got a solution to that linear system. Wx equals all ones vector, where W is our inclusion matrix for the complete case. Now, the next natural thing to say is that well, our graph is pretty close to under a high minimum degree assumption. Our graph is pretty close to KNNN, and so shouldn't it be the case that WG is approximately the same, and this linear system is probably not damaged too badly if we remove a few edges? Okay, so that's the moral of the sort of overview of the proof idea, is we're going to argue via perturbation methods that our system WG x equals all ones has a non-negative solution provided G is close to complete. And then we'll quantify how close it needs to be and interpret that in terms of minimum degree. So a little minor lie. For convenience, it's actually nice to work with the normal linear system. W transpose Y equals all ones. And so your vector X is just this W transpose Y. But now we have a nice symmetric, real entry matrix that we can non-negative integers, WW transpose that we can actually use for some, maybe investigate some spectral properties of it. In fact, we'll see in a moment that WW transpose lies in a nice adjacency algebra, or I guess, well, in a Bose-Messner algebra, and then we'll be able to solve this this slightly simplified system, which will imply a solution to our. Oh, by the way, notice we have a non-negative solution Y to this. Then because W is just a 0-1 matrix, then W transpose Y, this is my X that I really want, will be non-negative as well. Okay, just a little illustration. This is just a toy illustration because I mean, maybe things are a little nastier than this in general. But suppose you just have like basically the largest example I could fit on the screen here. So K222. WW transpose looks like this, where I haven't told you exactly what the indexing of my edges is, but the rows and columns are indexed by edges. And I basically just put in the IJ entry, or sorry, I should say maybe the EF entry, I put the number of triangles containing E union F. Okay, so say this is my E, and I don't know, this is my F, say here, then the matrix tells me, or this WW transpose tells me, okay, yeah, there's one triangle containing E union F. Now, of course, on the diagonal, you have 2 because it's K222, so every edge itself is in 2 triangles. But I can work with this matrix here. Now, what happens in the case where we blow a hole in our complete graph, right, is we have some missing we have some missing edges, right? So therefore we have fewer triangles containing the remaining edges. So say we remove a couple edges, well, we lose some, we not only lose those edges completely, those rows and columns completely, but we also lose some triangles that were there before. Now they're no longer there, okay? So some entries have been reduced and some rows and columns have been obliterated. So WG sort of damages our linear system in that sense. However, I want to show you a hope that it doesn't damage it too badly. Okay, so the perturbation tool we need is basically this relative error estimate. So if we have an invertible matrix and we want to solve AX equals B, but, well, we don't want to solve AX. Say we have a solution to AX equals B, but we want to solve a perturbation. So A plus delta A is our coefficient matrix. Now let's say that A inverse delta A isn't too bad, right? Its norm, P norm is less than 1, say. Then okay, well then it's the theorem, the lemma here guarantees that okay, A plus delta A is still non-singular under this norm assumption, and the unique solution to this square linear system has relative error upper bounded by a function of this norm A inverse delta A. And I mean, I guess the main thing we want to do is sort of interpret what do we need out of this to get non-negative solution. By the way, that in case that slipped by, that's an important point here, right? It's not hard to get a fractional decomposition into triangles, say, where you allow negative weights, right? That's not too hard. But the key point is we'd like to have non-negative weights, and so we need our relative error to be less than 1. Right, in our case, and so we need A inverse delta A to have norm at most 1/2. Now I'll tell you why, hopefully in a bit, why the infinity norm is chosen here. Although you could get away with, I think you could get away with a 1 norm, but basically the infinity norm is useful, or the 1 norm. These are going to be useful for us because our minimum degree assumption naturally translates into a norm assumption. Well, I guess a norm on the perturbation, a norm on the delta A. Is everybody still hearing me okay? I've had my Zoom kind of off the screen for a second. Okay. Any trouble, just unmute and interrupt, no problem. Okay, so the rest of the proof is basically just trying to use this perturbation bound. So we just try to get a bound on A inverse delta A, where I have to tell you a little more accurately what A and delta A are. But roughly speaking, they're just going to be those two big, you remember those two big 12 by 12 and 10 by 10 matrices I had before, WW transpose and its G analog. Okay. So basically this thing is nice and algebraic, and I know how to invert A, right? And this other thing is what I really want, but it's close to A. And so I should be able to get away with this game plan if I can like kind of do all my bookkeeping and, but okay, so yeah, the key point, I think I've already sort of said it, is that WW transpose is super nice, right? It lives in a nice algebra that's connected closely to the line graph of K and NN, which we'll talk about in a second. That's the real, I guess, meat of the algebraic graph theory here. So A inverse can be found explicitly, and so we can get a norm estimate on it, and then stick it into our tool that was on the previous slide, and hopefully get a sufficient condition for a fractional decomposition via a solution to this linear system, which involves WG, the perturbed version of this nice guy. Okay, so a little reminder about association schemes, although I don't need to really give the slide for you folks, but anyhow, just to set up the notation that I'll use. So we have a K-class association scheme is partition of our ground set cross itself into the symmetric binary relations. So they're indexed so that R0 is the identity relation. And then for any two, I mean, just to remind you of the structure constants here. So for any two elements in our ground set, if they are sort of H related, then the number of third elements that are simultaneously ith related to X and jth related to Y is a constant depending only on the indices H, I, and J, and not on the elements themselves. So in particular, each Ri is a regular graph, and I'll denote its degree by nu sub I, which is also the structure constant PII superscript 0. So a lot of this probably the details are a bit fast when we get into our structure constants and stuff, but you are familiar, I'm sure, with how the game works here. We set up an algebra of generated by the adjacency matrices of our relations, and because of the structure constants, we actually do indeed get an algebra. So the product of an AI and an AJ is just a linear combination of AH's via these structure constants here. So an important example for us is the Hamming scheme, which probably don't need to tell you about as well, but so the elements are bracket n, that's the set of elements 1 to n, Cartesian product with itself k times, so these words of length k in the alphabet on n symbols. And two elements in the scheme are declared to be ith associates if and only if their Hamming distance equals, this is, Hamming distance equals I. Okay, so in particular, when their Hamming distance is 0, they are 0th associates and they are equal words in this ground set. Okay, the scheme in which we want to work today is slight variation on this. So the Hamming lattice, which I found in a paper of Bill Martin from many years ago on product association schemes, and I don't know if there's a better name for this. And somebody interrupt if you know. So I'm going to actually look at a certain level in the Hamming lattice. And I don't know if this has a particular name. I mean, there's lots of various ways to kind of maybe to talk about this scheme, but anyhow, okay. So in the Hamming lattice, we have some we have a new symbol which we might think of as like a blank. Okay, so we have our n symbols and we have a blank, and then we take the words of length k in that, and then so now we have a whole lattice here because we have partial order kind of set up as inclusion. So x precedes y in the order okay, so basically x and y agree except for on the blank symbols, which x may have more blank symbols than y, but otherwise on the non-blank symbols, x agrees with y. And we're going to look at a certain level that is we're going to look at those words in the lattice with a fixed number of say r non-starred elements. Okay, so if we okay, so just to sort of connect that with what we're doing with our graph here. So the vertices, edges, and triangles in our complete three-partite graph, they correspond with the elements of rank 1, 2, and 3 in the Hamming lattice, where we have n symbols. And remember now, blank is allowed to kind of wipe out or to kind of focus us on rows, to focus us on a vertex or an edge or a triangle, depending on the level we're in. Okay, now our WW transpose, as we sort of pointed to in the picture before, this is just counting the triangles that are above a given two, that contain a given two edges, which in the interpretation here, counting the number of words with no blanks that are above a given two elements that do have blanks in the second level. Okay, now the second level of our Hamming lattice is a symmetric 4-class association scheme, and its degrees are given here. So, for example, this is saying that, now I guess I need to actually tell you what the relations are, don't I? Because without that, it's not too helpful. But okay, so let me explain the 5 classes if we include the identity. Say we have an edge E shown here, right? There are essentially 4 other types of edges that there can be relative to this E. You can be touching and in the same partite sets. You can be disjoint and in the same 2 partite sets. You can be touching and contact a third partite set, or you can be disjoint and in 2 different partite sets. So you have these I guess 5 relations in total. We could have E equals F, or we could have F as one of these other four possibilities here, okay? Now, with the, I don't expect you to remember it, but, and I'm sorry, these I think should be dashed and solid here. So sorry, yeah, dash instead of dotted, I think is here and here. Apart from that little typo in the figure, we've got these 5 types of relations between pairs of edges. Okay, so for instance, if we look at the nu sub 1, 2 times n minus 1, well, if we take our edge E here, we can have a first associate of it in, well, 2 ways to choose which sort of, which one of these 2 endpoints of E is going to coincide. And then we have n minus 1 choices for the other endpoint. Now, in the same way, well, I mean, maybe look at relation 2. You can see in relation 2 here, we need a disjoint edge chosen, edge disjoint from E, but chosen in the same 2 partite sets. So here the degree is n minus 1 quantity all squared. And so you can compute the degrees in this way. Now, here's something kind of nice, I guess. Our WW transpose is actually nicely sitting in this algebra as just n times the identity, which is also known as A0, plus A3. That's because every edge is in exactly n triangles, and the triangles that can possibly cover 2 edges are only, those triangles are the only other relation, I guess, that we can consider to have a triangle above them is this one here, that is the third associates. In that case, we have exactly 1 triangle when we specify 2 edges that are third associates. And so WW transpose is n times identity plus A3. So let's try to invert that matrix. To do that, we set up the structure constants like this, which can be done with some elementary counting or actually Krautchuk polynomials in more generality when you dial up the kind of order of things here. Okay, so we get those, and then we can. I won't bore you with all the details. We now can. Okay, so yeah, now we can find eigenvalues by again using. Sorry, here's where we use Krautchuk polynomials. I guess we can turn these adjacency these structure constants into eigenvalues, and we can actually find the eigenvectors too. I wish I had a little more time. It would be fun to tell you about the description of, for example, the kernel of our matrix, or the eigenvalue 0 case. But that is sort of important for technical reasons, because I'm lying when I say let's invert WW transpose. This matrix is actually not invertible, but we can do a little trick where we're going to translate it by a multiple of the projector onto the 0 eigenspace, eigenvalue 0, sorry, eigenspace, and then we can get a matrix that we can invert, and it won't change our linear system. So that's sort of the game, in case you caught that technical lie. That now, yeah. So what does this thing kind of mean? This eigenvector, just very briefly, this is sort of like an alternating force cycle, I guess, in our graph. And there's, like, I guess, nice interpretations for the spectral features in this Hamming lattice, second level of the Hamming lattice. So hopefully you believe me that you can do some calculations in this lattice and get the quantities you need in order to invert our suitable matrix for our linear system. Okay, so there are the eigenvalues kind of written out in terms of, well, they're showing up, I guess, in these projectors, E0, E1, E2. I mean, I'm sorry, this is kind of just naive application of standard methods. But I guess, unlike, I mean, most of these nice talks I've seen in the seminar series, which, by the way, I think is awesome. Thank you to the organizers and to people who've spoken so far about. Most give some contribution to algebraic graph theory. I'm sorry, I'm just a shameless user of it, and I only have some modest result which uses it. But I think that might be interesting, because the uses may motivate some new theory. The main idea, I guess, is here that we are I think the one interesting feature here is that we're sort of marrying the idea of the algebraic, the nice algebraic object with a perturbation, right? So if you ever have a structure that maybe is close to algebraic and you want to study it, then you can probably do so with the perturbation tools. Anyhow, if we let K, sorry, I'll go back. If we let K be projection onto the kernel of WW transpose, then if I, now there's sort of a choice of a constant here that's sort of best, but if you let your coefficient matrix be WW transpose plus this certain multiple of K, then you get you can invert this matrix. Well, now you've kind of lifted its eigenvalues. So okay, you get this bound on the infinity norm of the inverse. Okay, and then the perturbation itself, I guess I don't have a lot of time to tell you about the details in that, but it's really just some simple counting. Delta A is just going to kind of tell us, it's just going to basically do the bookkeeping of what are my missing edges, and basically missing triangles. The triangles that get broken by removing the edges going from the complete graph KNNN, complete three-part digraph, to our locally balanced, almost complete graph G. And so with minimum degree assumed to be say 1 minus epsilon times that of the complete graph, then 6 epsilon n is your infinity norm upper bound. I guess, yeah, I mean, maybe there's time to just sort of mention, remember how there's some missing rows and columns. So in fact, that like our matrix, you might say, well, wait a minute, Peter, your matrix actually reduced. It went from, in that example, it went from 12 by 12 to 10 by 10. But what you can kind of do is like put a frame around your matrix so that, let's see how this works. I guess we're going to organize our rows and columns so that the removed ones occur, let's say, here on the right. Okay, so this is my WG. And then, well, maybe A plus delta A, let's say. No, I guess it's delta A. So yeah, A plus delta A is going to sort of occupy, well, A plus delta A is going to occupy, I guess, the whole thing. So, but we're going to organize it so that 0 is sort of this block 0 matrix here. And then below, these last rows and columns are kind of, we can just sort of stick what was in our matrix A. So they're kind of like corresponding to the missing edges that got removed. But I only really want to solve a linear system whose coefficient matrix is up in this sort of upper left here, which is most of the size of the thing, right? So anyhow, with that norm bound on A inverse and the perturbation, now we use the submultiplicativity of the infinity norm, and A inverse delta A gets upper bounded in norm by 46 over 3 epsilon. And we need that to be, remember, less than a half. And if it is, then we can get, because of the perturbation tool, we can get a solution to our linear system, and therefore a fractional K3 decomposition of our graph. I should just mention one little point. This, if you do a little mental arithmetic, this is going to give epsilon about 3%. And you can get it a little bit better to 4% by doing something a bit better than this submultiplicativity here. You can get a little bit better result if you just directly bound A inverse delta A, but I won't bore you with those details. The main idea, as I say, is that you can use perturbation with our almost algebraic inclusion matrix for for the edges versus triangles in our graph. So you can generalize this a little bit to say cliques of size k in a k-partite, almost complete, locally balanced graph, and get a threshold there. The order is about k to the minus 4 for the epsilon, and you can even generalize to the sort of t-uniform hypergraph case, and you get a threshold there. And with sort of, I guess, decreasing amount of detail, we've got sort of a threshold there as well. Improvements for these should be possible, although we weren't too motivated by anything other than, for the moment, the Latin square completion. But if you wanted to complete moles or orthogonal arrays or something, I guess the technology is in place to do that. And yeah, I think maybe you could generalize the idea to other schemes. Maybe that's a possibility for future work. So you want to get some kind of decomposition or sort of maybe design-like thing in a setting where not all on the case of here we have edges falling into copies of a given graph, but I mean it should maybe generalize to maybe subspace schemes or something like that. There are the key references, and thank you very much for your time and attention, and sorry I'm a little late.